In this video, I want to look at how to verify trigonometric identities. To do this, let's start by discussing the basic trigonometric identities, the fundamental identities you might hear them called. So one set we have are the reciprocal identities, and these just stem from the reciprocal trig function, so sine is equal to 1 over cosecant, and conversely cosecant equals 1 over sine, cosine secant, tied together, and tangent and cotangent are reciprocal partners. We have our pair of quotient identities. Tangent is equal to sine over cosine. Cotangent is equal to cosine over sine. Pythagorean identities, sine squared plus cosine squared equals 1. That's the basic one that I always remember. We can generate the other two by dividing off sine squared or cosine squared. So if we divide all the terms in this first identity by sine squared, we would have sine squared over sine squared, which is 1. Cosine squared over sine squared, which is cotangent squared. And then 1 over sine squared is cosecant squared, so that would be the last of the identities there. And then if we divide everything by cosine squared, well, sine over cosine is tangent, cosine over cosine is 1, and 1 over cosine would give us secant, and then they're all squared. And then we have our even-odd identities, sine being an even odd function rather, so if we take sine of negative theta, it's equal to negative sine of theta, cosecant also an odd function. Cosine is the even one of our basic trig functions, so cosine of negative theta equals cosine of theta, meaning secant is also even. Tangent negative theta is equal to negative tangent theta is an odd function, so cotangent is as well. Then the cofunction identities, remember we can use 90 degrees or pi over 2, it does not matter, but we can go between sine and cosine, they are cofunctions, by taking our angle and subtracting it from pi over 2 or 90 degrees. Cosecant and secant are cofunctions, and tangent and cotangent are cofunctions. So we'll use these basic identities along with just our basic mathematical abilities too, to simplify more complex trigonometric expressions. So to do this, we're going to work with these keys. And the book lists some steps or some keys off themselves, and a lot of our keys kind of overlap, but I don't like to number these because we're just going to make sure we keep everything in mind at any given time. The trick to these is it's almost like a puzzle. When we go to verify these identities, it's like a puzzle because there's not just one right way to do a puzzle. Some people like to do the edge pieces first, other people might group them by color, by shape, or by size, and everybody has their method for doing it, and there's many ways to arrive at the correct answer. As long as we are, doing things mathematically correct, we can't just hammer two pieces together that don't fit. We need to make sure that we're following kind of some guidelines as we go through the problem. So the first key is we only want to work with one side of the equation at a time. We're not going to work across the equals. We're trying to show that the statement is true, and so the second we're working across an equals, we're potentially assuming something that's not true. We're going to start with the more complex side, and that seems kind of counterintuitive until we recognize that, hey, it's much easier to simplify, to cancel things out, or to add, subtract things that will simplify, than it is to grow something out of nothing. So we're going to start with the more complex side. We just want to follow the math, and this is my way of saying anytime we see addition, subtraction, multiplication, division, exponent, square roots, anything that we see that we can do, we want to do that. Simplify wherever possible. Follow the math. A lot of times when we get stuck, it's helpful to have everything in terms of the same thing, and so we can write things pretty easily in terms of sines and cosines using our reciprocal quotient identities, or simplifying angles using maybe cofunctions or even odds, and then we're going to have other formulas that we add to this as we go through the course that will give us more tools at our disposal to be able to simplify or to manipulate the angles, and that's the last key, is to make sure the angles match. And so right now, the only way we have really of messing with the angle is using our cofunction identities, but we're going to gain more tools as we go forward that will allow us to manipulate the angles. We're going to do several examples. I want to start very, very simple. So we're going to verify the following identity. So we have tangent theta is equal to cosecant theta equals secant theta. Now, when I read off those basic identities, I did not read all the thetas just to save some time. But I want to always write my thetas inside my trig functions, or it might not be theta, it might be alpha or beta or x, but the key is I want to make sure I'm always writing down what that is, because if those angles aren't the same, which they aren't always going to be the same, then eventually we're going to have to make sure we get them to match. So we always want to write down the angle, whatever we're calling it. All right, so the first thing I want to do is I want to pick a side, and it's definitely looking to me like this is a more complex side. There's just more to it. So I'm going to start by writing down LHS, standing for left-hand side, and that's just making it extremely obvious to your reader what you are doing. These are a little bit different because we know exactly what the answer is. We know the answer is going to be secant. Your your work is not trying to get to an answer. Your work is explaining why this statement is true. And so uh, I'm your teacher, or whoever your teacher is going to be reading through these, and they have to be able to follow your work. So I'm going to make everything extremely obvious. So I'm starting with the left-hand side. I'm only going to work with this expression. If I think about what I can do, well, obviously these two things are multiplied, but I don't really see any way to simplify those in their current form. Um, Kind of comparing apples and oranges right now, it'd be really nice if we had all the same trig function to be able to relate, and that's why we a lot of times want to write things in terms of sine and cosine. So I know that tangent, I can write tangent as a sine theta over a cosine theta. And to do that, I have to use the quotient identity, and I'll write that in just a second. And at the exact same time, I'm going to go and change cosecant over. Cosecant is 1 over sine theta. And I don't mind if you do a couple steps in one, as long as you're not doing it to the same function. So for instance, obviously these are going to cancel. I'm not doing that in one step though, because I want to see, I want to be able to follow that work. I want to see what you're really doing. And so now what we need to do is we need to write out what we used. So off to the side here, right to the right of my work, I use the quotient and the reciprocal ID. And so it doesn't have to be a great long explanation. I need to just be able to follow what's going on. And so what we said just a second ago, very clearly those signs are going to cancel, and that's going to leave us 1 over cosine. And so formally what we did is we multiplied or we divided there. You could write divide, simplify, any number of things you could write as long as it's mathematically true. So we divided by the sign, or we multiplied by the reciprocal, it doesn't matter. And then finally, 1 over cosine is secant theta. And we know that is true because of our reciprocal identities. So we actually used a pair of reciprocal identities in this problem to show that this statement was true. And the second that we have that right-hand side or whatever side we weren't working with, that is when we know we are done. We need to have that exact expression as we see it. Let's look at a second example. Here we have sine squared x is equal to secant x minus cosine x over secant x. First step is to decide on the side, and it's definitely seeming to me like that right-hand side is a more complex side. So for my reader, to make it very clear what I'm doing, I'm writing down RHS, standing for right-hand side, just rewriting what that was too. My goal is to have a sequence of steps that take me from one side to the other. So this should be my end goal. Now, there are a couple things that I see that I could do here. Some people really like to go to sines and cosines right away, and that is fine, right? That is not a bad step. Sometimes it can add in a little bit more work, or sometimes it can just add in a couple steps, and that's fine as long as we get to the answer. It doesn't matter how quickly we do it. So I think converting these to cosines, that would make sense. The other thing I see is that I could, if I wanted to, break this up into two fractions and maybe simplify there too. So either of those makes sense. We are trying to get to just one term, and so maybe for that reason we'd think, hey, I want to leave it as one fraction. So I'll write this in terms of sine and cosine first. I know that secant can be written as 1 over cosine x. We do have x's this time, not theta, so I do want to make sure that I'm keeping that x and not using any other variable. And so what we did here is we just applied a reciprocal identity. Then what I see is I have fractions and fractions, and this is where I'm just kind of following the math. I never like fractions and fractions. That's never okay to leave an answer as a fraction and a fraction. So let's see what happens when I get rid of those fractions and fractions. If I want to get rid of the cosine in the denominator of the numerator and denominator, I need to multiply every single term by cosine. I hear some people say, well, we could also multiply by the reciprocal. That is true. Just the danger in that is we have two terms in the numerator, and so we have to be really careful that we distribute to both those terms. Or the bigger problem is if we had multiple terms in the denominator, then there wouldn't be necessarily just one reciprocal to multiply by. We'd have to get common denominators first. So I prefer just to multiply by whatever the common denominator is. I'm going to multiply every single term by cosine. So 1 over cosine times cosine is 1. Cosine times cosine is cosine squared. And then 1 over cosine times cosine is, again, just 1. And so here we multiplied top and bottom by cosine x. 1 minus cosine squared over 1 obviously is just 1 minus cosine squared. Don't necessarily care that you write this out. I think that's all pretty obvious. If we stated that in the previous step, we could have simplified both in one, but I'm just making sure I make it very obvious to you guys what I'm doing. So we divide it by 1, which of course just keeps it the same. And so then if I'm looking at this, we've got it pretty simplified, but my goal was to get it to a sine squared. Well, anytime we see these squareds, Pythagorean identity should be jumping out of the paper at us. And so let me just off to the side here. This is not part of my formal work. This is just kind of some scratch work. I know that sine squared x plus cosine squared x is equal to 1. And somehow that's involved, but that's not what I see in front of me. Well, we can always rearrange equations, right? This Pythagorean identity, this is a true equation. We've shown that to be the case. So now that I know it's true, I can rearrange it any way that I want to. So if I want to see 1 minus sine, that means I need to subtract this cosine over. So sine squared would be equal to a 1 minus cosine squared. Squeeze that in. And that's exactly what we have, and so we know that the 1 minus cosine squared, coming back to our problem, that is just sine squared x. So those Pythagoreans, they're a little bit different. They'll kind of sneak up on you because we're not always comfortable, or we're not used to being able to change squared terms. We want to remember anytime we see those cosines or sines, they can go between each other if they are being squared because of the Pythagorean theorem. Also notice that every single step I have has a label next to it. Every single step has an explanation. I need to see that, otherwise you're not going to get full credit for your problems. Let's take a third example. We have tangent x over 1 minus cotangent x plus cotangent x over 1 minus tangent x equals 1 plus tangent x plus cotangent x. Left-hand side looking significantly more complex to me. So there's a few steps again that we could take here. On number 2, we talked about the fact that there are multiple right ways to start off. I think one thing you could do is change them to sines and cosines. That would be potentially a good first step. Could also maybe get a common denominator, because if I'm looking at this, I have 2 different fractions, 2 different terms that I really want to turn into 3 terms. Probably at some point I'm going to need a common denominator. Doesn't have to be right away, right? It might be, but it doesn't have to be. So let's start. We'll change them to sines and cosines, because if we're really not sure, or if we're not completely convinced that we need a common denominator, changing things to sine and cosine is not a bad start. So I know that tangent is sine over cosine. I know that cotangent is the cosine over the sine. And same thing over here, cosine over sine, 1 minus sine over cosine. And we have our x's on all of those. We used, of course, our quotient identities. If I look at this, I don't like the fractions within fractions, so I'm going to get rid of those. And if I look at what's going to be required, in my first fraction here, the numerator of the denominator is cosine, the denominator of the larger fraction is sine, in the denominator of the denominator is sine. So I need to multiply every single term by sine and cosine. The common denominator across the whole expression here is sine cosine. That's also going to be true over here, but I only have to look at one fraction, or each fraction individually, but the common denominator, sine, cosine, so I'm going to multiply everything by that fraction. When I multiplied this numerator by sine cosine, the cosines would cancel, but I would have sine times sine, which is a sine squared. When I multiply this one, I do have to remember to do it to every single term, so I have to multiply this one by sine cosine, and nothing is going to cancel. We have sine x cosine x. And then I multiply this third term by the sine cosine. The sines would cancel, and that would leave me cosine squared x. I'll do the same thing over here. So when I multiply sine cosine, the sines would cancel, leave me just cosine, cosine squared x. Then I would have the sine cosine. And then when I multiply this one, the cosines would cancel, leave me a sine squared. So my explanation here, I multiplied by the common denominator, or I multiplied by sine x and cosine x, there we go, on top and bottom. I like to do the explanations as I'm going because that way I don't forget about them. I'm doing them as I go. So at this point I have some options. I could get a common denominator and try and add these things together, but that common denominator would be this whole expression times this whole expression. That's really ugly. I'm just thinking it's probably not gonna, I don't want to do it. And a lot of times that's a good indication that if there's something that just seems like it's gonna be terribly ugly, probably don't want to do it. So what I'm gonna try is I'm gonna try and factor out anything that I can. I know on the bottom I can factor out that cosine x. That'll leave me sine x minus cosine x. On the second one over here, if I'm just concentrating on the pieces I can factor right now, I can factor out a sine, and that would leave me a cosine x minus sine x. Now that's a little bit better, because now I'm starting to see some elements in the denominator that are kind of looking a little similar. And so that way my common denominator is going to be a lot less ugly. The other thing I might go ahead and do, I'm going to do it right now, I'm going to fully factor this thing. I want them to match, so I'm going to pull a negative out of this second one too. That'll allow me to switch this to be sine minus cosine. That way they are in fact the same. So here we factored. So let's see what our common denominator will become. If I write down just the common denominator, well, I have that cosine sitting in front of the first fraction, so obviously I need that cosine x there. The second one, I have the sine, and it's going to have to be a negative, or really I can just pull that negative to the front if I want to, right? I'll worry about that in a second. But I need that sine x down there, and then I have the sine x cosine x. Sine x minus cosine x, there should be a minus in there. If I think about how I got that common denominator, well, this one was missing the sine x, so this is going to become a sine cubed. And this one was missing the cosine x. And the reason I pulled the negative there is because we talked about pulling that negative out of that sine. So that negative I'm just pulling up here with the cosine. So we'll have cosine cubed there. And so now we have added with a common denominator. Now what's jumping out at me is the top is the difference of perfect cubes, and so I can factor that. The top would factor as sine x minus cosine x, sine squared x plus sine x cosine x. And then I would have my plus cosine squared. All over our common denominator. So this does require us to remember how to factor perfect cubes. So if you don't remember that, look that up. But this is just using our a cubed minus b cubed equals a minus b, a squared plus ab plus b squared formula. I need to finish my parenthesis there. And so once we factor, then what we see is this sine x minus cosine x is the same in top and bottom, so I can actually cancel those off. And the really nice thing about that now is I only have this single term in the denominator, and that's going to make things a lot easier. So what I'm going to do is I'm going to go ahead and break it up into 3 different fractions. And it's a long time since we started this problem, so we may have forgotten, but remember we were trying to get to something that had, all the way back up here, 1, 2, 3 different terms. So we're trying to get something that had 3 terms. That should have been a sine squared. And then we have our sine x cosine x, And then we have our cosine squared x over sine squared x. And so to recap what we did here, we canceled or we divided and wrote as 3 fractions. We can always break apart to the denominator. We can't break apart, saying that a little bit clearer. We can break apart the fractions if the denominator is one term. If we have multiple terms in the denominator, kind of how we started, we're not allowed to break those things up. So coming back up to this point, I couldn't write it sine squared over this and sine squared over that. We have to have a single element in the denominator to do that, and we did at this point. Now I see a lot of things that cancel, and so let's start canceling those. The sine in this first one we can cancel off, so we'd have sine x over cosine x. The second one, everything cancels, it's just 1, and then we have I wrote that last one wrong. Let me go back and correct that. So a lot of times things will jump off the paper at you when you mess up because you know what you're supposed to get to. So that was supposed to be cosine squared over cosine x sine x. But this gives me a good opportunity to talk about the fact that, hey, I would have just written that as a cotangent squared, and that was clearly wrong. So we knew that wasn't a key of our final answer. I need to go back and see what I did wrong, and I just copied that last bit wrong. I can cancel off the cosine zone. I'm going to have cosine x over sine x. So here again we can write simplify, cancel, divide. Let's say that we divided here. And at this point we are just nearly done because remember we were trying to get to tangents and cotangents, and sine over cosine is tangent x. We have our 1 there, and then cosine over sine is cotangent x. And we used the quotient identities. And so if I look at my original problem, what I was trying to get to, way back up here, 1 plus tangent x plus cotangent x. That is the same thing that we have. Ours is not in the correct order, and so I am going to request that you put it into the correct order. By the time we get done, it should match exactly with what we're trying to get to. 1 plus tangent x cotangent x. And this seems a little bit picky, and I know not every teacher requires this, but what I see a lot of times is you'll get to that last step, or what you think is the last step, and it'll look nearly like. And there will be something that was wrong in it, but you didn't pick up on the fact. So make sure it is identical to what we were supposed to have. Now, it wasn't. How did I rewrite it? I rewrote it using the commutative property or the transitive property. You can say either one. If I could spell. Commutative or transitive property to rewrite it, but make sure that you convince yourself there is something mathematically possible or mathematically sound reasoning for rewriting it. A lot of times I see that negatives will kind of suddenly switch positions. So for instance, it may have been 1 minus tangent, it should have been tangent minus 1. Those two things don't just magically switch. Here, because we have all addition, that is why we're allowed to switch these. So I do want to see that you're using some sort of mathematical principle to rewrite to have exactly what we're looking for. So hopefully these 3 examples give you a pretty good idea about how we can approach our verifying trig identities. They are not all quick and easy, right? This one took me a little bit of time. Now, there's a good chance you could have done it more efficiently. So please do look for other ways to do it, or if there's something you said, hey, why couldn't I have done this? This seemed like it would have been faster. Try it. See if you get the right answer. You're going to know if you have the right answer, not when you get to the final step, because you have to end up with what we should have. So there are lots of different ways to approach these, lots of different steps you can take. The key is we only want to work with one side at a time. We want to make sure we are explaining every step. Now, if you really get stuck on one side, it is okay to kind of restart the problem on the other side, see if you can work it to a point where they get them to match, but we don't want to work across the equals. That's very important. I only want to work with one side at a time.